Questions about anything? So last time I introduced complex integration, and in the process I had to first come up with a simple kind of integral that involves functions, complex functions of a real variable. That's step one because that's a part of the definition of the complex version. So we got two kinds of functions now, the analytic ones that we've been studying. Those are complex valued functions of a complex variable, usually defined on a domain into the complex plane. Now we've got a new kind of function, which are complex functions of a real variable, z of t. And we think they'll be most useful in parametrizing curves in the complex plane. So you could think of the x of t and the y of t as the parametric equations for a curve. And so this kind of function maps an interval on the real line into the complex plane. And we've got two kinds of derivatives now. One is the complex derivative with the complex difference quotient limit, leading to the definition of analytic functions. And the new one is the derivative z prime of t, which when you write out the difference quotient, you realize, oh, that would just be a derivative of the real function part and plus I times the derivative of the imaginary part of the function. So that's straightforward. Then we start talking about two kinds of integrals. I define these in terms of Riemann sums, limits of Riemann sums. They make good sense. The simplest one is the integral of a z of t dt between a and b. It's just the real integral of the real part and the I times the real integral of the imaginary part. You see that just by splitting the Riemann sums into real and imaginary parts. But that led to something new, and that was the definition of the complex integral of f of z dz along a curve. And that's defined in terms of the previous kind of integral. So I would calculate f of z of t, multiply by z prime of t dt, multiply it together, and then I'd have integrate that in terms of the definition of the previous kind of function, namely a complex function of a real variable. That's what that is. And so if I was going to calculate that with my bare hands, I'd multiply that out into real and imaginary parts and then do that calculation. Okay, that's the definition. I motivated that as a Riemann sum limit, and I didn't get too bogged down in that. I didn't want to get carried away with it. But you think of this z prime of t dt as a dz. If I wrote dz dt for that z prime of t, then that would be dz dt dt, leaving you with a dz. Anyway, that's how you remember that formula. And the next, let's see, I proved these last time. There's two kinds of chain rules. One is the one for analytic functions that's very similar to the freshman calculus version. And the new one is when f is analytic and you stick a z of t in it and get f of z of t. If you differentiate that now as a function, complex function of a real variable, then you get an exact similar chain rule, namely f prime of z of t times z prime of t. And those are two different kinds of derivatives. The f prime is the complex difference quotient definition of derivative, and the z prime of t is the new kind we've been talking about. Okay, that was a rather straightforward thing to do. I used the Cauchy-Riemann equations to do it. And now the new thing today, I promised I would show you there's two fundamental theorems of calculus. And they're going to be very straightforward. I'll demonstrate them in a second. In that number 2 there, that's a curve gamma that starts at A and goes to B. And so that would be the integral along that curve of f prime dz is f at the endpoint minus f at the starting point. So I guess I should draw a picture here. This curve would start at A and go to P. And that's, I'm denoting that gamma starting at A going to B. Okay, and let's see. I proved the number one basic inequality there last time. That's a very simple thing. It's just taking the modulus of a Riemann sum and realizing you've got a triangle inequality. And so that basic estimate for that kind of integral is the maximum of the modulus of z of t along the curve times b minus a, the length of the interval. Okay, that's going to lead to the basic inequality number 2 for integrals along curves. That'll be look kind of similar. That if you call this max m, it's the same kind of thing. You take the maximum modulus of f along the curve, and you multiply by the length of the curve. Okay, that's the length of the curve is in place of b minus a. Anyway, those will pop right out. So let me start with the demonstration of the fundamental theorems. Okay, so here's fundamental theorem of calculus number 1. Let's see, so we'd have integral from a to b. There's nothing to this one. This one is just freshman calculus fundamental theorem. That would be the integral from a to b of x prime of t dt plus I times the integral from a to b of y prime of t dt. And you know the fundamental theorem of calculus for real functions like this. This would be x of b minus x of a. And this one would be y of b minus y of a. And when you add those together, you realize, yes, sure enough, that's equal to x at b, a z at b, rather. That'd be x of b plus I y of b minus z at a. So check. There's nothing to that one. Fundamental theorem of calculus number 2 is slightly more interesting. Now, because we have to use the number 1. Okay, so that's the integral along gamma that starts at a and goes to b of f prime of z dz. By definition, that's the integral as you go along the parameter space of f of z of t, f prime of z of t, times z prime of t dt. And when you stare at that for 2 seconds, you realize, oh my gosh, that is the chain rule formula. That's d by dt of f of z of t, our new chain rule. One of our new chain rules. And so by the fundamental theorem above, that would be equal to f of z of b minus f of z of a. And sure enough, that is f at the end point minus f at the starting point. So check. Questions about that? Yeah.
So I guess when you write the two types of functions that you're saying, is it because one of them is in terms of a real variable
Right.
rather than
Right.
z
So when we're talking about parametrizing a curve, we got a real t, which I like to think of as time, because it's chasing out a curve as the time goes on. Okay, so yeah, I got two kind of functions to deal with. But they're highly related, of course.
And when you write it in terms of a real variable, it's because it's like separable, basically?
No, it's just a one-dimensional thing. When you integrate along a curve, it's a one-dimensional integral. And we have to make sense out of Riemann sums of complex numbers, which we can reduce to real things. And after we get comfortable with that definitions, we'll stop doing that. Other question?
Just to clarify, if you have a closed curve.
Yeah, that's going to be great. So what you observe there is if we have a closed curve, the starting point and the ending point be the same, which means the integral of f prime around a closed curve is going to be 0. That's going to be a thing. In fact, I'm going to sort of dwell on that in a minute. Let's see. Okay, so that leaves me with one last thing I have to show. The basic estimate, number 1, I did last time. Basic estimate, number 1. That was the easy one last time. I just did the triangle inequality on a Riemann sum. But the basic estimate number 2 is new, and I need to explain it. Let's look at the modulus of integral from a to b. Let's see, what am I doing here? I don't care what the ending points are. Sorry. Integral along gamma of f dz. That stands for the integral from a to b of f of z of t, z prime of t, dt. And now I'm going to use basic estimate number 1. So this is basic estimate number 1. That's now reduced to the kind of integral that's the simple kind. So that's going to be less than or equal to the max of oops, what am I doing? I don't want to do the max yet. This is less than or equal to the integral from a to b of the modulus of the thing inside. Okay, interesting thing about this modulus here, that is the square root of x dot squared plus y dot squared. That should be a familiar thing from sophomore calculus. That's the element of arc length. Okay, and this will be, let's say this is less than or equal to m. And I'll tell you what that m is in a second. Okay, this is actually the inequality I used when I proved the basic estimate number 1. So I just basically took the triangle inequality underneath the integral, across that integral in the Riemann sum. Okay, do you believe that one? That's just a write down. Okay, so this is going to be less than or equal to, I can pull that m outside the integral, and then I get here the integral from a to b. that modulus of z prime of t is x prime of t dt squared plus y prime of t squared. And that's just the dt. That's the element of arc length from sophomore calculus. That's ds. And so that integral is just the length of the curve. You could take that symbol as to be the definition of the length of the curve, but it's what you're familiar with from sophomore calculus and the length of a curve. Okay, so the last thing I need to do is tell you what that m is, where m is the max of f of z of t as t ranges from a to b. Which I would say I would define that thing as the max along gamma of the modulus of f. That's a shorter way to write that same thing, but it's the same idea. Because as z of t traces out the curve, you get the maximum modulus of f on the curve. Okay? Questions about that? Yeah.
I was a little confused. What's the difference between fundamental theorem 1 and 2? It seems to be the same thing.
I used the fundamental theorem to get I used number 1 to get number 2. So yeah, number 1 is the basic one, but you know, I've got these new symbols I have to make sense out of, and so yeah, they're highly related, but I need one to get the other. And number 1 is the easy one that you just need freshman calculus to think about. Does that answer your question? Let's see, here's an important fact. I've been doing this assuming my curves are C1 smooth. So I've been assuming gamma is C1 smooth and F is analytic in a neighborhood. Well, let's see. I don't need to talk about F just yet. And what that means is that x of t, y of t, and x prime of t, y prime of t are all continuous. Those derivatives exist and are continuous. On the whole interval. So even up to the endpoints. Meaning they have left and right derivatives from the two endpoints. And it's a fact, it's not hard to show, it's easy to generalize our facts to piecewise C1 curves. And here's what that means. I'll give you a picture definition. Piecewise smooth curves. And so they look like this. They can have corners, but they can't jump. All right, so I start someplace, I go up in a C1 curve, and then I can have a corner. Like that. And then maybe I could have more corners. Oh, and I guess I can even intersect myself if I want. But corners are allowed. So there'd be finitely many intervals where I'd have C1 curves, and then I'd stick them together at the corners. So this curve would be continuous, but our corners are allowed. Continuous, but finitely many corners. So in the book, you'll see a definition where you split up the parameter interval into segments, and you've got left and right derivatives at the corners, et cetera, but there's the picture. So, but finitely many corners are allowed. Okay, I won't write out the gory definition. But the fact is that our facts hold for that kind of curve. So the basic facts hold for piecewise C1 curves. Okay, and let's see, so why is that? Let's see. Here's an example of one of them. Example, let's integrate along a piecewise C1 curve of f prime dz. Then I would split that into segments. So I'd get, when I do that, I'd get finitely many segments, and I'd integrate along those segments. So gamma sub n of f prime dz. And each one of those segments would have a starting point and an ending point. And so that would be, when I do it, I use the fundamental theorem on the first one. I get f at the end point of that segment minus f at the starting point. And then the second segment, I'd get f at z3 minus f at the starting point, which would be z2. And one more, f of z4 minus f of z3 plus dot, dot, dot. Let's see, the last one would be f at the ending point, call it zn, minus f at zn minus 1. And when you look at that, you realize, oh, this is a telescoping sum. So let's see, this z2 would get eliminated by this. F of z2 would get canceled by that one. This f of z3 would get canceled by this one with a minus, et cetera, et cetera, et cetera. This one would get canceled by something. And there'd be two that don't get canceled, namely the starting one and the ending one. So let's see, this would be the ending one right here, and this is the starting one right here. And so this would, in the end, this would be f at the end point minus f at the starting point. So the telescoping thing gets rid of all the junk in the middle. So that's all there is to that. That's a standard. Okay, but now that we know all these facts, I can go back to that example. Let's calculate this time I'll take it going from minus r to plus r. So here's 0, here's minus r, here's to plus r. And this is my curve of radius r, circle of radius r, which I like to parameterize by z of t equals r e to the it, as t goes from 0 angle to pi. And now look at this. My z of t is equal to r times e to the it. I told you I'd never write that again, but I'm going to do it today because I'm going to use the chain rule to calculate z prime of t is r e to the I prime of t, e to the prime it times d by dt of I times t, which is just I. And so we get here r, e prime is itself, and this would be the derivative of I times t is just I. And so the z prime of t is I r e to the it. Let's put that in a box because that's something you got to know for future calculations. You don't actually have to use it in a future calculation for calculus-like, but when we make estimates, when we estimate various things, we'll need to put that thing in there in the proper form. And so now the example I wanted to show you was let's integrate along c sub r. How about e to the 2z dz? That would be the integral from 0 to 2 pi of e to the 2 r e to the it, and then dz would be I r e to the it dt. And last time I demonstrated how ugly that is. I could write it out in all its gory detail and contemplate splitting it into real and imaginary parts. But now today I can use the fundamental theorem of calculus, so this is better. Let's see, this would be the integral of a derivative, and the derivative is d by dz. You know, the antiderivative of e to the 2z is 1 over 2 e to the 2z. And so that's equal to 1/2 e to the 2z evaluated between the starting point and the end point. This end point is minus r. The starting point is r. So that would be 1/2 e to the minus r minus 1/2 e to the r. What is that? That's equal to minus the hyperbolic sign of r. What?
I think you lost the 2 in the exponent. Yes.
I did? Oh, yeah, why did I do that? Thank you. So it would be minus, this would be a minus 2r plus 2r. And so it would be the hyperbolic sign of 2r. Okay, so now we're getting close to some exciting ideas. Coming soon is Cauchy's theorem. Cauchy's theorem, namely that if f is analytic on a domain with no holes, with no holes. There's a word for having no holes. Okay, so we haven't defined holes in a mathematical sense. So the fancy math word for that, a simply connected domain. That's what it means. That's the math word for no holes. then the integral around every closed contour of f dz is going to be 0. They're closed, meaning they start and stop at the same point. In omega. And that kind of means you've got to study the complex integral, because when it comes to analytic functions, that turns out to be sort of a defining feature of them. And in fact, we'll see that there's a converse thing. So the funny thing is the reverse is true. The reverse is true. In some sense, I got to be careful about what sense it's true. If f from omega to c is continuous, so you can make sense of those integrals. It's continuous on a domain omega. You don't even have to think about simply connected in this case. On a domain omega, and the integral around every closed contour is 0. All closed curves in omega, then f is analytic. And the moral of the story is we have to study complex integrals. And it's going to turn out to be a really good idea because it's going to lead to a whole bunch of fascinating things about analytic functions. Okay, well, it'll take me some couple days to demonstrate this thing. It's not going to be hard. And the book has 2 different ways of going about it. I'm going to choose sort of the vector calculus way of doing it. 4.4b is the Green's theorem approach. That's a vector math 261 kind of thing. Green's theorem approach. That's Cauchy's theorem. That's what we're going to do, and we're going to skip the other version, which is called the homotopy version. Skip 4.4a, for now at least. That's the homotopy approach. Homotopy means deforming curves. I see a question, yeah.
The theorem, the first one, does that mean that f is the derivative of some function?
Yes, we're going to get to that in a second. That's highly related to Cauchy's theorem, especially on a simply connected thing. If an integral around a closed contour is 0 for all curves, then that function is the derivative of something. That's what I'm going to show you right now. So here's a big fact. Let's suppose f is analytic on a domain and the integral around every closed okay, here's what I want to say. then f has a complex antiderivative, or I should say has an analytic antiderivative, capital F. So I guess that means meaning that f prime equals so meaning that the complex derivative of capital F is little f for all z in the domain. That's an if and only if the integral around every closed contour is 0. So if and only if. So we've got two-way implications here. If and only if integral around gamma of f dz equals 0 for all closed curves gamma. In omega. And one direction is a snap. You've already made note of it. So the proof is this direction is easy. So that's meaning we assume f prime equals f. That's what this direction means. Assume capital F prime of z equals f of z. And assume gamma is closed, which means then when I calculate the integral of f around a closed curve, that's going to be the integral of a derivative, and that's going to be f at the end minus f at the start. And because gamma is closed, these are the same points. And so that's a big fat 0. And that's all I have to check. So that's really easy. Just the fact. The other way now is the one I got to think about. It's not going to be hard. Let's see. This time we assume the integral around f, around a curve, its closed curve, is 0 for all closed gamma in omega. Okay, so now I'm going to start thinking out loud. So if I had an antiderivative, so this is a hypothetical, if I had f with f prime equals little f, here's what I could do. Here's my omega. No mention of holes, so it could have a hole. I could take a curve that starts at A and goes to a point Z. I'm thinking of A as being fixed, and maybe I'm going to let Z slide around. And so I like to call this curve a gamma that starts at A and goes to Z. If I had a thing like that, then I could write integral along gamma from A to Z of f prime of w dw would be equal to f at z minus a constant. When you're differentiating functions, constants don't matter. Okay, so when I stare at that for a second, I realize, this is f of w, and this is a constant if I fix a. And we think of a fixed, and we slide z around. If I had the f, I see a formula for right there. So when I take the derivative here, I'm still thinking out loud. Adding a constant doesn't change the derivative. So I would get an f prime of z equals d by dz of the integral from a to z rather, of f of w dw. dw. Because the derivative of a constant is 0. Okay. And f prime of z was equal to f of z. And so the antiderivative is this thing. This is what we want. Okay, I'm done thinking out loud now. So the big idea now that I've been thinking out loud is we kind of know what we want. Let's define. Don't know if I'm going to get away with it yet, but I'm going to define my f of z to be fix a point A, integrate along a curve that starts at A and goes to z of f of w dw. I've got two problems to deal with. Number one, I would have to show it's well-defined. Step one. That's going to be easy. Show f is well-defined, meaning it makes sense. That turns out to be easy because of the hypothesis. Okay, I'll do a picture here to make it so you see why it's easy. I've got my blob, omega. If I have two curves, start at A, end at Z, okay, so let's call this one gamma A to Z, and let's let this one be gamma A twiddle. This is going to be a twiddle one. So that'll be gamma A to Z twiddle. I've got two curves. If I let, so the aha here is, let's let, here's my own personal notation, capital gamma, I'm going to go out by this curve, A gamma, A to Z, and then I go back by the other curve. That's a closed curve. And so the integral around gamma of f dw is 0 by our hypothesis. That's the hypothesis we've made. The integrals around closed contours are 0, and that's equal to the integral from gamma from A to Z of f dw plus the integral going backwards And you remember when I did the Riemann sum of difference, I added up things. When I defined the complex integral, it'd be a Riemann sum. If I go the other way, those things would be interchanged, and it would give me a minus sign. So this is an easy fact that follows from the definitions. This is equal to minus if you go the other way. That's an easy fact that pops right out from the definitions. That's something you learn in Math 261. When you go along a curve, it's if you parameterize it going backwards, you get minus that integral. That's basically the fact here. Okay. And so that means that those two integrals are the same. And that's exactly, if I pick a different curve, starting and stopping at the same spot, I get the same thing. That's exactly what it means to be well-defined. Check. Questions about that? Okay, so the last step is I need to show, and that's, maybe I'll save, I've been done enough technical things today, I don't want to get overwhelmed by it, but step 2, now that I've shown it's well-defined, that's the hard part, actually. Step 2, I need to show that f prime is what it's supposed to be, capital F prime. And that's going to feel very much like the freshman proof of the fundamental theorem of calculus. I'll do it next time. And it's going to feel like freshman calculus, which is one of the cool things about complex analysis. It's going to feel like freshman calculus. Remember when you took d by dx of the integral from a to x of h of t dt? You drew the little area under curve, and then you had x plus x plus delta x, and had that little tiny sliver. Let's see, x naught equals h of x naught. How did that feel? I had a graph. This goes from a to x naught plus delta x. And then when I would have these areas, those would represent areas, and when I subtracted them, I get this little thing here. And because h is continuous, when I divide by delta x, it's the height of that little thing. And that height of that little thing, area divided by delta x, is approximately the height of that rectangle, and that's approximately h of z x naught. So that's the freshman calculus proof of the fundamental theorem of calculus. It's a fun lecture because everybody believes it's true. It's going to feel like that. So I'll give you something to anticipate for next time. It's not going to be hard at all. Any last minute questions about anything? So homework 4 is due Thursday night. Okay, that's enough for today.
My homework for physics.
I'm like, well, I'm gonna go home
Wednesday at like
another
so I'm probably going to be working on it until like 2 or 3 a.m. on Thursday.
No, it's not bad.
Hopefully not need all
And then I'll do my math.
There's something that's a little crazy.